Hi again, wanted to make another video on half-lives and double times, but this time we're going to change up the information that is given versus the question that's being asked. So let's say, totally hypothetical situation, but let's say that let's say we take some medicine and let's suppose that the medicine we took is a 20, oops, wrong highlighter, is a 20 milligram pill. And we are told that this medicine will now start to be processed or decay in our body at a rate of approximately, let's just go 8.3% each hour. So totally made that situation up. But you can imagine with me, you take a 20 milligram pill, your body now starts to process it at a rate of 8.3% every hour. Okay, so the question might be, what is the half-life? So if we are asked to determine the half-life of this medicine, half-life of this medicine, then how are we going to set that up and how are we going to solve it, especially in this stage in the game in this course? So if you go back to in our slides, there's this slide that kind of summarizes the relationship for you. So our skeleton formula for half-lives is change factor raised to some unit of time. And for a half-life, you're of course wanting that change factor to amount to 0.5 or 50%. So in this particular context, what are they trying to tell us? So we know that it decays 8.3% every hour. So with that knowledge, we can figure out the change factor. So remember that your change factor is always 1 plus, or in this case, it'll be minus the rate. So for this particular context, the change factor will be 1 minus, since it's a decay rate, that decimal percentage in decimal form would be 0.083. And so the change factor for this situation will be 0.917. Okay, so now that we know the change factor for this context, let's go back up here and figure out what we know versus what we don't know. So the change factor we now have figured out is 0.917. But here's the thing. I don't know what the half-life is. I don't know the unit of time. How long will it take for this medicine to be at 50% of what it was? This is the question that we're trying to answer. We know the change factor. We do not know the time. So you'll notice I cannot simply solve for t right now using normal operations. I can't take a square root because the power is not 2. I can't take the 10th root because the power is not 10. I don't know what kind of root to take. That's just it. We don't know the exponent. So eventually we will learn logarithms, which are the inverse operation of exponentials. Eventually we will solve this algebraically, but for now, we want you to solve this using intersect method. So if you imagine this entire thing right here, that's a decreasing exponential function. I can put that into Desmos in line 1, and it will produce a decreasing exponential function. And the question becomes, when does that function reach a value of 0.5? Notice the 0.5 is on the outside of the equal to bar because 0.5 is our desired output. So y equals 0.5 is what's going to go in Desmos line 2. And this, friends, is how we're going to solve this function or this equation. So I'm going to hop into my Desmos. And in line 1, I'm going to put our decreasing exponential function of 0.917 to the power of I don't know what. So there's the decreasing exponential function as my body processes this medicine. It's going to decay at that rate. And we are here to find out when the output value reaches that 0.5 for the half-life. And you'll see that you can figure out just by looking at the graph, when does that particular function reach its half-life of 0.5? And in this case, it's at exactly 8 hours. So back, it's not usually a whole number. That's crazy. I got lucky, you guys. I made this problem up and it came out as a whole number. What? Don't count on that in the future. It's usually decimals. All right. So if we go back here, we found out that it's going to take 8 hours for this medicine to have its half-life. Now you could, just for the record, you could set this up in all of its glory. So the entire full exponential function would be 20 as the initial value times that 0.917 to the power of t. But please note, if you do set it up this way, you'll be wanting to intersect it with, well, I guess there's two options here. You could set it up like this, in which case you'd be intersecting with exactly 10 milligrams because 10 is exactly half of 20. And so that's another way to solve it. So let me just show you how this would work. If we were to incorporate the initial value of 20 times, there we go. So now my initial value is there, 20 times the 0.917. Well, now for the half-life, I'd be wanting to figure out when it reaches 10 milligrams. And you'll notice that I now have to adjust my window in order to see numbers like 10 milligrams and 20 milligrams, but it still occurs, look at that, at 8 hours, exactly 8 hours. So if you have the initial value, you can incorporate it. But I think one of the cool takeaways is you don't have to. You could totally be asked to find a half-life without even knowing the initial value. Just so you know, you do not have to be told the initial value. Notice in the skeleton here, there is no initial value in that skeleton. And the reason why is algebraically, if you come back down here, if we were trying to solve this equation algebraically, the very first thing we would do is divide by 20 in terms of inverse operations that we do know. But if you divide by 20, guys, what is 10 divided by 20? Spoiler alert, it's 0.5. So that's why you end up at the exact same place as what the skeleton would have told you. So whether you intersect using the initial vertical intercept, of course, intersecting with exactly half of that value, okay, that's an option, or just forego the vertical intercept, use the skeleton that we have, and you'll get the same answer. So kind of cool. All right, hopefully that's helpful. And again, for now, this is the method we expect to see in your work. So please be consistent. Do not Google stuff. The internet has so many ways of doing this, and they are not consistent with what we're learning. So please focus on this way, do them this way for now. Okay, thanks, guys. Appreciate your time, and hopefully it was helpful.